And yeah. So this is called figuring out what electronic circuits do and making electronics remember past events. Okay. So here's an overview of today's lecture. I'm going to recap very briefly last lecture. So I'm going to try and recap all lectures very quickly. I'm going to recap logic gates. We're going to have a little mini quiz. Then part of this lecture is going to be called figuring out what digital circuits do. And what I'm going to teach you here is basically a general technique for figuring out what digital electronic circuits do. So this isn't sort of a simple technique that will just apply to these circuits. This will apply to all circuits. And then I'm going to talk about memory and making electronic circuits remember things. Okay? And this is a very, very big and important topic. And you won't be able to design sort of robots and things like that unless you know how memory elements work. So in that context, I'm going to talk about flip-flops and serial to parallel converters. So last lecture, I explained the difference between what I'm teaching you and what Arthur's teaching you. And I said what I'm teaching you is basically the brains of electrical engineering. I'm teaching about electronic engineering, and Arthur's teaching about electrical engineering. So basically the stuff Arthur's teaching about, basically if you plug your fingers into it, you'll die, okay? So like 500 volts, 500 amps, big, big, nice voltages and currents that you can do useful work with. And what I'm teaching about, in effect, is the brains of electrical engineering. And, you know, I'm teaching you to make circuits, to make those smart decisions that decide when to turn Arthur's circuits on or not, okay? And I tried to split this up and demonstrate this last time. I showed you this example of a robot, and I said in general, the actuators on the robot's arms and legs, so here and here, these are all going to be electric motors. And these will be sort of, you know, relatively high voltage, relatively high current. And on the top of the robot, you've effectively got sort of electronic circuits. So there's going to be a computer in there, so that'll be electronic circuits. There'll be some logic gates. You know, there'll be sort of the smart electronics that makes the robot clever. And I just told you effectively how we can start to store information in electronic circuits. So I said that, generally speaking, if you could just sit down without making a huge fuss, that'd be brilliant. Thank you. Any seat will do. So generally, I said the sort of international definition of a 1 in electronics, or of storing a 1, is a circuit being on. And the international definition of a circuit being off is a 0. So sort of, you know, even with a light switch in a room, you can store a 1 and a 0. If you turn it on, you're storing a 1. If you turn it off, you're storing a 0. And I said this is why on all devices, basically, so on that computer, there'll be a 1 0 button, so on or off, because on is always 1 and off is always 0. And I said what you can do is combine lots of light bulbs, so sort of circuits, in parallel like this. So we can have 1, 2, 3, 4, 5 light bulbs. And what we can do is if we label each light bulb 1, 2, 4, 8, 16, so notice the numbers doubling each time, so we're going from 1, 2, 4, 8, 16. Can you guys see? If I stand here, maybe that's better. You can store any number you want. So, for example, if in this electronic circuit you wanted to store the number 21, you would turn on light bulb 1 representing the 1, light bulb 4 representing the 4, and light bulb 16 representing the 16. And then if you add all these numbers together, so 16, 4, 1, then you get to 21. So using this, you can store any piece of information. And this is how all electronic circuits store information in this way. So if you open your mobile phone, it'll have a series of 32 wires connecting all the chips together. And these are the wires that transmit digital information. Each one of these wires will be worth 1, 2, 4, 16, all the way up to 2 to the power of 32. Okay, so that's general information storage. And I said storing or writing sort of digital information or numbers out using light bulbs is a very, very long and tedious process. I said a much quicker way to write this, so you might be sort of doing this in an exam, would be to represent the circuits being on or off with 1s or 0s. So a 1 represents the circuit being on, and a 0 represents the circuit being off. So, and a 0 represents the circuit being off. So you can write any sort of number representing with a series of 1s or 0s. And this is called binary, and it's called binary because there's only 2 digits in the counting system. There's a 1 or a 0. It's like a bicycle. A bicycle's got 2 wheels. A binary's got 2 digits. And we did this little example where I told you sort of how to teach how to count in binary. And we counted from sort of 0 to, I think you did 16. And this is a very, very useful thing to be able to count in binary because, of course, if you want to generate all possible patterns of ones and zeros between, say, for, say, 4 bits, if you just count up in binary, that will naturally generate all possible combinations of inputs to the circuit. So this is very useful, and we'll use this in a minute, and we'll find out. So there's quite a long tail of people coming to this lecture late, and so if you could try and be here on time, please, because it's immensely disruptive. So if you're more than 10 minutes late, just don't come in, or just go and sit outside because you're disturbing the lecture for the people, like these people. Okay. I'll repeat it in a minute. So I've just said to the people who are here that there's been a very long tail of people being late. So if you're more than about 10 minutes late, I'd appreciate it if you didn't come in. Okay, so if you just stayed at home, because there's no point. Okay? So now I want to do a mini quiz. So, whoops-a-daisy. So we looked at these AND gates, and I said AND gates come in a chip like this. So this is a picture of an AND gate, and each Who likes disruption to the lecture? Is it irritating, or is it just me that irritates? Is it irritating? Yeah, so maybe talk to your friends and say don't come in late, okay? So last time I taught you about this AND gate, and I said it only gives you an output. It only gives you an output of 1, so an output here of 1, when both inputs are high. So when you get a 1 and a 1 going into the AND gate. So an example of this I gave you is Burglar alarm circuit, where you had 2 inputs A and B, and it gave you an output of Q. And you only got the output going high when both A and B were on. So what I'd like you to do now, I've just shown you the answer, but I'd like you to jot down, I'd like you to fill out this truth table on a piece of paper. So just write down this truth table. Do it as quick as possible. It's just a really, really mini quiz, so I'm only going to give you about 20 seconds for this. So finish up this truth table. Go for it. Good stuff? Good. Hello. How are we doing? How are we doing? What we got? You haven't got it? Who's got an answer up here? Who's got an answer? You done? Yeah, good stuff, good stuff. How you doing? You got it?
It's 0, 0, 0.
Okay. All right, I see a few people with it. Whoops. Okay, so this was the answer. So those of you who didn't have your pens out were too slow. So this is the answer. Whoops. Whoops. This is the answer. Chaps, guys. This is the answer. So it only goes on to 1 when both inputs go high. Okay. I'm going to give you another one. This time, try to remember it. So this is an example of an OR gate, and the output only goes high, or it goes high when either of the inputs are high. Okay. So whenever you put a 1 into the left-hand side of the OR gate, the output will go high. Okay. So the truth table is 0, 0, it goes off, 0, 1, it goes on, 1, 0, it goes on, and 1, 1, it goes on. So it's on if any input is high. So write that out. Just scribble that out, see if you can do it from memory. And I'm making you do this, even though I've just shown you the answer, because I want this embedded in your memory. Because the whole of the next lecture, the next 3 lectures are going to be on these AND, OR, and NOT gates. So just try and see if you can do that from memory. So who's got that done from memory? Go on, what have you got? You done it? Perfect, excellent. You done it? Let's see some answers. Very good. Okay, so I think so I think people have got the hang of that. And the final one I want to remind you of, whoops. You want more time? You're done. You're done, okay. The last one I want to remind you of is this, chaps? this NOT gate, okay? So the idea of a NOT gate is it inverts the input. So when you put a 1 into it, it gives you a 0 out. And when you put a 0 into it, it gives you a 1 out. So the truth table looks like this: 1, 0, 0, 1, okay? So when the switch is open, it basically produces an output. So now just try and jot that down, just really quick, just note it down. I'll give you like 10 seconds, okay? Right, so I'm assuming you've done that. There we go. So this next section is called figuring out what electronic circuits do, okay? Now, so far, I've taught you the most simple electronic circuits with AND gates, OR gates, and NOT gates. And we've made things like burglar alarm circuits, circuit fire engines, very, very, very simple circuits. Now, when you want to build more complicated devices like that robot there, you need to make very, very complicated circuits. And very often you need to figure out what a complicated circuit will do. So, for example, somebody might give you a diagram of a circuit, and they might say, what does this do? So what I'm going to do now is teach you a general technique to figure out what circuits do, okay? And this is very useful. Who, by the way, has seen this Boston Dynamics video? One? Okay. Who would like to see it? It's pretty cool. Okay, we'll just watch this video. Right, here we go. So what this is, you can think about this, is basically the top of this thing's full of sort of electronic engineering. So, you know, clever electronic circuits that we're basically learning to build now. And the bottom's going to be full of sort of higher voltage stuff, so motors and actuators and things. Right, watch it. So it's quite good at sort of recovering its own balance. And this is all, of course, happening with this electronic engineering. Now, but what you didn't realise is, look at this surface. This is ice. This is actually skiddy ice. This man here is actually having trouble walking on this surface, but the robot recovers its own balance. You see, look how careful he's being. Yeah, and it goes on and on. Yeah, so that's pretty cool, the use of electronics and robotics and stuff like that. Okay, that's enough of that. Right. So back to the lecture. So very often you might, so all these circuits in these robots are made by joining these AND, OR, and NOT gates together. And I've laboured the point about AND, OR, and NOT gates. But you can build effectively all chips out of AND, OR, and NOT gates. These are sort of the key functions. And even if you think it's sort of you know, a fancy Pentium processor, it's still going to be made of the same AND, OR, and NOT gates. So what we're going to do is we're going to analyse. We're going to spend the next 10 minutes or so analysing this circuit here and try to understand what it does and producing a truth table for this circuit. Now you might think, oh, he's just joined a lot of gates together to make a pointless circuit. But this is not true. This is actually called an Xor Gate when you consider all these components together. And this is used as a fundamental component of addition and sort of all arithmetic operations inside modern computers. So your phone will have millions of these little circuits in them. Oh, I know what. My pointer's not on the screen. That's it. Right. So let's start off. So I might give you a much more complicated task in an exam or something, but let's start off with this quite easy circuit to understand. So this is how we analyse any electronic circuit, any one that's given to you. Okay. Whoops. So let's start off with, sorry, my pointer's come up. Let's start off with this circuit here. What you do, first of all, is you label the inputs and you label the outputs, okay? So this circuit's got two inputs. It's got an A and a B, and it's got an output of Q. So you've got two inputs and one output. And you can probably guess what this circuit does now, but this general strategy will teach you how to analyse any circuit. So here we go. We basically write A and B are the inputs and Q is the output. then on the input, all you do is you count up in binary. Okay, so you go 0, 0, 0, 1, 1, 0, 1, 1. And what this will do is this will give you, just by counting in binary, all possible combinations of the 1s and 0s on the input. Okay, so if you evaluate the circuit at all these inputs, you've defined the whole circuit. There is no other combination of inputs that you can give it. Okay, then what you do is the following. You take one line of the truth table. So in this case, I'm taking the third line just because it's the most interesting line. Okay, you'd probably start off with the 0th line in an exam or something, but I'm starting off with the third line because it's the most interesting. And what you do is you write, often in pencil. It's often good just to write this in pencil, to write 1 and 0 on the input of your circuit. Okay, and then what you do is you propagate these 1s and 0s throughout the circuit. Okay, so what will the value be at the purple arrow? 1. Okay, and you can do that because you've now practiced at all gates. Okay, so we've got a 1 there. Now, a NOT gate inverts, so what will the output there be? 0, right? So you write that in the truth table. So you've now defined one line of your circuit. And we can continue this process, working our way through this circuit, and we find out that this circuit produces this output. Okay, any questions so far? No? Good. And this will work. This simple principle will work with any circuit. So you can sort of, try it with any circuits in some complicated robot, some complicated cruise missile, and you'll be able to define what the outputs are for any given set of inputs. Okay, so it's quite a powerful method. So let's look at this more complicated circuit now. So this is sort of more exam fodder maybe. So firstly, we've labelled the inputs. We've got A and B, and we've labelled the output. So we write our truth table, and if it had 3 inputs, then you could just have a third column here, and it would be a lot longer. And what we do is we start just literally propagating these numbers through the circuit. So let's start off with the top row now. So we pop 0 here and 0 here. Now it's a bit complicated, so we've got to decide which logical path to follow. So what I'm going to do is I'm just going to propagate this 0 all along this wire, and it gets to 0 at the input to this AND gate. Okay. Then I'm going to, so I don't know what the other input to this AND gate is. So I'm going to propagate this 0 all along this wire here to the NOT gate. And what will that be there? 1, right? So now I've got a 0 and 1 going into an AND gate. So what will the output there be? 0. We've got a 0 going into the OR gate. Now we still don't know what the output of the circuit is because if this is 1, then we could still have an output of 1. So let's look at the other side of the circuit. Propagate the 0 from there to the side of this AND gate. Propagate this 0 to the NOT gate. What's the output there? 1. What's 1 and 0 going into an AND gate? 0. What's 0 and 0 going into an OR gate? 0. So we now write 0 on our truth table, okay? So you can do this for every line of the circuit, and you can define the outputs, okay? Now, circuits can get very complicated, but this process will work. Okay. So it's your go. I'd like to fill out the rest of this table in like 3 minutes. So in fact, just have a go at this top line, okay? Just have a go at this top line, because I don't think we've got time for the rest. It's all right. The notes are on the internet. You don't need to take pictures. It's all on Moodle. So just have a go at the top line. So just try tracing through this circuit with the 1s and 0s. I'll give you a couple of minutes. And even if you can't do it, you'll benefit a lot by trying. So I recommend you have a really good go. Looking good? Looking good there? Yeah, good start. Yeah. So a good trick to start off is just draw the circuit out firstly. Just have a go at drawing it out, and then write the A and the B. Yeah, exactly. Good stuff. Yeah, have a go. You'd be much better to have a go. So draw the circuit out to start with, then just have a play with it with a pencil. Good stuff. Good stuff. So I would really have a go at this. Good stuff. You all right?
Yeah, I'm just looking.
Okay. How are we doing? Any of you got an answer for me yet? Any of you got an answer? No? 0? You don't know? Who's got an answer? Who's going to be the first with the answer?
One bit will give 0 and the other will give 1. A and B, I mean.
Have you got the answer?
I haven't got an answer.
Okay.
I'm just asking a question about the question.
I'll come back to you. You can ask me afterwards. You done it? What have you got? Oh, you done it all? What'd you get? 0? What'd you get? 0, 1, 1, 0 is the answer. So the man at the front here has done it all. He's done all rows of it. So the answer is 0, 1, 1, 0. Who got that? Hooray! Well done. Thank you very much for trying. Okay. So this circuit here, as I said previously, this circuit here is called an Xor Gate, and it's a very, very useful gate, and it's used in things like addition, subtraction, in all types of computers. So this is a real electronic circuit that you use all day, every day, and it wouldn't, modern world wouldn't work without it. So I'm now going to talk about making electronic circuits remember things. So you can see we're getting through this quite quickly. I'm teaching you quite simple methods, but you already know how to analyze digital circuits. We're going to cover memory in the next like 5 minutes, 5–10 minutes. So we're really, really cracking through this syllabus, even though it might seem simple. So flip-flops. So far we can basically count. We can make simple decisions, so we can make fire alarm circuits, things like that. And we can detect the position of our robot with a shaft encoder. But what we can't do is we can't make it remember things. And to make any type of intelligent device, you basically need to have it to remember things, because it needs to know what happened in the past to decide what is going to happen in the future. So we now need to talk about memory elements, okay? So just think in your head, firstly, about these OR gates. So here's the OR gate here, and it's only going to be 0 if it's got 2 zeros going into it. If either of the inputs are a 1, it's going to give you a 1 at the output, okay? That's all very easy, very, very easy. Now think about this circuit. So just think about this in your head. So if we put a 0 in the input, and we have a 0 on the output, and we have a 0 on this input, the whole circuit is going to be 0. If you talk, it makes my life much more difficult, so please don't. And in the set and sem forms from the MATLAB, people wrote, oh, he interrupts us, he tells us to stop talking. Well, I can't concentrate on the lecture if you're talking, and it makes my life really difficult. So please don't, because it disrupts the learning experience for everybody else. So think about this circuit. So at the moment, we've got 0, 0, and 0 here. Now, think about this. This is just a thought experiment. Have this in your head. If you put a 1 into it now, we change a 0 to a 1. What's going to happen here? 1. This 1 will get fed back round here to here. And now we've got like an infinite loop of 1. Okay? So no matter what we do to the input there, we've still got this 1 going round, and it's stored this 1. So we've now remembered, the circuit remembered that it's had a 1 at some point present on the input. And the only way we can actually stop it remembering that it's had a 1 on the input is to kill the power and unplug the circuit. This is called, effectively, so here's this animation. We put 1 or 0 or 1 or 0. The output will always remain 1 because it's got this loop, this sort of trapped 1 in it, okay? And this is called a latch. The word for this is a latch, because you know when you close your front door, it latches. It like remembers it's been pulled shut. And you can never open it again without a special key. So this piece of circuitry is called a latch, okay? And this is a timing diagram. So if you're an electrical engineer, a proper electrical engineer, I would spend ages going through timing diagrams with you. But I'm not going to. What I'm going to do instead is just tell you what they are. A timing diagram is effectively the output of a digital circuit. So here we've got A, which is the input. So input A, input B, and Q. Okay, so inputs and outputs. And what I've done is effectively plotted over time, so this is time, the outputs or the values of these letters. So here we've got A. When you see A goes high and then low. So somebody has made this go high and then low. So high and then low. And then B, as soon as A goes high, because the output of Q goes back round to B, as soon as A goes high, B goes high, and forever it's 1. So that's our latch, okay? And also because Q is attached to B, also Q goes high, and it's latched on forever. So this is called a timing diagram. So very often when you have a digital circuit, somebody might say, draw the timing diagram of this circuit for the following inputs. And this shows that you really understand what's going on in the circuit. Any questions about timing diagrams? We'll have a little practice at those in the examples class on Friday. Okay? So, the only way of making this circuit reset is to turn the power off. And this isn't very good because if when you have your computer, you need to rewrite memory all the time. You save a Word document, you edit the Word document, you need to change those ones and zeros all the time. So this isn't a very good type of memory. So the way to stop it remembering a 1 is to put a little switch in this feedback loop. So you just push the switch up, and this feedback loop is broken. It's no longer got a 1 going on the input, and you've reset the memory element, okay? Now, this is a bit of a cumbersome way of resetting a memory element. So what you actually do is you do something like this. Now, I know this looks a bit scary, but don't be scared by it. Firstly, pick out what you can understand, what you know about. So we recognize this. What's this? And, right? What's this? Not. What else can we see? We can see some feedback. There's some feedback wires here, and they look a bit like this thing here. We can see some inputs. It's got J, K. It's got the output of Q and Q bar, and something called cluck that I'll tell you about in a minute. It looks complicated, but we can understand those components. And I'll tell you what this is. In effect, what this is this circuit, but with a slightly more complex way or a very sort of useful way, effectively, of killing this feedback loop. So that's what this circuit element is. And if you had a computer sort of from a while ago that had been stuffed full of these things, like that very nice computer down there. So yeah, we can recognize various components. Now, because this looks a bit scary, and I don't really want you analyzing circuits like this with feedback because it just gives everybody a headache, what I'm going to do for the rest of this lecture is stick all of this, so all of these elements, in a box, okay? And we're just going to treat it as a box. And the box is going to have inputs of J, K, and outputs of Q and Q bar and clock. And it's just the same as this, but I've just hidden the detail. And in electronics, you often do this. You have a super complicated circuit, and you say, well, I can't be bothered handling that circuit. I'm just going to treat it as a black box, basically. Now, this particular device here is called a flip-flop. And it's called a flip-flop because it flips and it flops back between, effectively, 0 and 1 or 1 and 0. So we think of it as a flip. It's like flipping flip-flop as you walk along. And the outputs can either be 0 and 1 or 1 and 0. And this might seem a bit arbitrary, but I'll explain this in a minute. And these are the input pins. So we've got J, clock, and K. And the output pins are Q and Q bar. And I'll explain what Q bar means in a minute. So the idea of this flip-flop is to remember things, okay? So if you put a 1 on the input J, I can't remember what's going next, actually. Right, so what we're now going to do is we're going to store a 1 in this flip-flop. And to store a 1, what you do is you put a 1 on the J pin. You then put a 0 on the K pin, okay? So J is like the number it's remembering, okay? And then what you do is you apply a pulse to the clock pin, okay? Now this might seem a little bit abstract, but I want to explain, I think I do it in this slide, what a clock is. Now, in a clock in digital electronics is basically something that makes things happen. It synchronizes a circuit. So you know when you buy a mobile phone, it says it's got a clock of a gigahertz or something. That means in your phone, there's a signal that looks like this. So it's going 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, about 1 billion times a second. And that's called a clock. And on the rising edge of this clock pulse, so when it goes from 0 to 1, something always happens. So it either adds a number, it subtracts a number, but the whole circuit is basically synchronized to this clock. It's not a clock like that. It's just a string of pulses that's used to synchronize things. So we go back to this flip-flop. We want to remember a 1. We've put a 1 on the J pin and a 0 on the K pin. So what we do to make this circuit remember this 1 is we apply a clock pulse, a single clock pulse. So we just go off, 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 on, bang, then off. And on this rising edge here, so as we go from 0 to 1, what will happen is this flip-flop will remember what's been put on the input, so it remembers. And the 1 that's been put on the input goes to the output, and it's stored. Okay? Now, no matter what we do to the inputs now, so no matter what we do to J and K, we can put 1s on it, we can put 0s on it, whatever. We can do anything to the inputs. The output will never change because it's busy remembering that 1. Okay? Now, if we want to store a 0, so it's storing a 1 right now. Now we want to go back and store a 0. So we put a 0 on the J pin, so we want to remember the 0. And we put the opposite on the K pin. So we've got 0 and 1, and this tells it to remember a 0. We then, what do we do next? You can probably guess. Clock pulse, right? So we apply a clock pulse. And then the flip-flop goes, you've applied a clock pulse. So I must remember what's on the input. It puts what's on the input on the output, so it's remembering the 0 now. Then no matter what we do to the input, we can put 1s and 0s on the input, do whatever we want to the input, it will just remember that 0, because it's busy remembering that 0, until you apply that clock pulse again. So what is this? So what is this Q bar pin? What does this mean? So in digital electronics, a bar means the opposite of, okay? So if I write 1, that means 1, quite clearly, okay? But what's the opposite of 1? So if I write 1 bar, what's the opposite of 1? 0, okay? So if I write 0, what's the opposite of 0? 1. Okay, so bar means the opposite of, always the opposite of, okay? So it's just a notation for meaning the opposite of. And we'll cover some of this more in the examples classes. So you can notice that basically this is the output Q, and this is the output Q. And because this is called Q bar, this output always gives the opposite of Q, okay? So if Q is 0, Q bar will be 1. If Q is 1, Q bar will be 0. Okay? Any questions? Any questions? Shout if you've got questions, please. No? Obvious? Okay. So there's 2 cases we haven't thought about. We haven't thought about the case of putting 0 and 0 on the input, or 1 and 1 on the input. We'll cover the 0, 0 case, because that's easiest now. So if we put 0 and 0 on the input and apply a clock pulse, nothing happens. It's defined that nothing happens, okay? Nothing happens to the input. It just doesn't do anything, okay? However, if we put a 1 and 1 on the input, so a 1 and a 1, and apply a clock pulse, what the flip-flop does, it flips, because it flips the 1 and the 0. So if you had a 1 and a 0, and you apply a 1 and a 1 to the input, it'll flip the output, and you'll get a 0 and a 1. So it just like flips the output. Okay, it's quite useful. So this might not seem practically useful at the moment, but when you're designing really complex circuits, this can actually be sort of a time-saving device. So this bit of flipping can actually be really used to your advantage. We won't go into that just yet, but we'll see later. So here's the truth table of a JK flip-flop. So here I've put the input, so 0, 0, 1, 0, 0, 1, 1, 1. So here we've got 0, 0 is no change, 1, 0 is set Q to 1, 0, 1 is set Q to 0, and 1, 1 is flip. So if you remember this table, you'll be able to remember the operation of a JK flip-flop without remembering that complicated circuit, and you'll have that, okay? Any questions about JK flip-flops? Okay? And you can buy JK flip-flops in packages like this. So, on modern computers, you'll have maybe lots integrated into some circuit. But if you just want 2 or 1 JK flip-flops, you can go to the shop and get a 7473 chip, and it looks a bit like that, in fact exactly like that, except it's just got the number 7 and 3 there. And you apply some power to it, and then you've got these like 2 little flip-flops. So if you're building for your group design projects, or for your, your 4th year projects or whatever, and you want like a little bit of memory, a couple of flip-flops, you can go and buy it for 20p, and you have a circuit that can remember stuff. And it's a slight bit of a sort of push to say you get these flip-flops in lots of modern devices, but you get them in certainly CPUs, and they're a general type of memory element. There's lots of different types of memory element I could have taught you about today, but this is a very, very general memory element that's very useful for digital electronics. So you'll find if you open a sort of a digital electronics book, there's a whole zoo of these things with different truth tables. But this is a fairly general type that's useful for you guys. Right, serial to parallel converters. We've got one more topic we've got to cover in this lecture. Now we've got flip-flops. So if you look at any modern computer, so for example, this is probably a computer, this microphone transmitter, or if you look at my mobile phone, this is a little computer. Inside it, connecting all the chips will be 32 wires, and each one of these wires, as I said previously, represents a number between 1 and, in this case, it would have 8 wires, so it would be an 8-bit computer, and it would have 8 wires representing numbers. So sort of connect various bits of memory, you'd always transfer, so you have these numbers to transfer data between various chips. And in modern things, it's about 32 bits. Generally speaking, your Apple Mac there is 64 bits, so it's got 64 wires connecting everything to transfer data and to store stuff. This robot, 32 bits, your phone's 32 bits, generally speaking. So you can think of all these devices having many wires in parallel inside them to transfer data between internal components. And another advantage of having many wires sort of in parallel to transfer information and to represent information is you can transfer information very, very quickly and efficiently, because you're transferring sort of all these bits at once in one go. Okay, so if you want to transfer the number 8, you just sort of turn on your switches, and you have your various lines high or low, and the information's there instantly. Now, if you look at the end of your mobile phone charger, it'll look a bit like this. So this is a USB cable. So if you sort of peer down the end, and typically it's got so if you don't think about the fancy USB 3 standard, so the typical USB 2 standard pin looks a bit like this. It's got basically 4 wires. Okay, it's got a power, so positive and negative, and that's what charges it. Then it's got a clock pin, which just has a clock. It's just like that on-off signal to synchronize information. All this will be on Moodle, so don't worry about noting things down. In fact, it should be there already. And then you've got this data pin, and this data pin transfers information. And you notice there's not like 8 wires to transfer information simultaneously. So if you want to transfer, for example, this number down that USB cable, what you do is you transmit this value, then 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 this value. And that's called transmitting information in serial, because it's in series, one thing after another. So you go 1, 0, 1, 0. You just shoot these 1s and 0s down your cable, and they'll be flowing out this data pin to your phone or to whatever your printer or whatever's plugged in with the USB. Now this is a very slow way of transmitting information, but they do it because it saves copper. So if you imagine your MacBook there has 64 wires transmitting the data in it. If you imagine a USB cable that has 64 wires to 64 bits of copper to transmit information, it'd be really expensive, and the cable would be about that thick. So that's why they do this. So what we need to talk to a robot here or to talk to your mobile phone is a serial to parallel converter. Okay, so it turns this serial information of 1s and 0s going down the cable into a parallel data stream that your computer or your phone can read. And this serial parallel converter, you'll find it in loads of electronic devices, and it really is the most important thing of almost any device. And what we're going to do now is we've now got enough knowledge to actually make one of these. So I'm going to show you how a serial to parallel converter works and what's in it. And you can guess what component's probably in it. It's called a JK flip-flop. Now, looking at this circuit, you might think, my goodness, that's horrendous. But it's not actually horrendous, because you understand all the elements already. So we've just been through the truth table to this JK flip-flop. So you know that, okay? Or when reviewing the notes, you'll know that. And at each of these outputs to the JK flip-flop, I've put a light bulb. So this represents the information that's stored in parallel. Now, this is how a serial to parallel converter works. So we're going to step through it bit by bit. So if you focus, you'll understand it. So on the input, we've got J. So this is where the data comes in. And remember, from the truth table of a JK flip-flop, you put the 1 here and a 0 here to store a 1. And you put a 0 here and a 1 here to store a 0. So this pin is always the opposite of this pin when storing data. Okay? So just focus on this bit, and you'll totally get this parallel serial converter. So if we put a 1 on the input of our JK flip-flop, okay, we then apply a clock pulse. Boom. And what happens is this JK flip-flop takes this 1 and remembers it and transfers it to here. This JK flip-flop takes this 0 and transfers it to here and remembers it. This JK flip-flop takes this 0, remembers it, and transfers the output to here. This JK flip-flop takes this 0 and transfers it to here. So what happens is we sort of shuffled along the data in this serial to parallel converter. So we'll finish the animation. So now, after the clock pulse has been, we've now got a 1 here, because we remembered the 1, and all these are 0, okay? We now set the input to 0. What do we do next? What do we do next? Begins with C. Clock pulse, right? So we put a clock pulse, boom. This JK flip-flop remembers this 0. This JK flip-flop remembers this 1. This JK flip-flop remembers this 0. This JK flip-flop remembers this 1. And all the 1 sort of shuffles along this register. This is called a shift register. So what happens is, boom. So we've now remembered this 0, and we remember this 1. So now, let's put another 1 on the input, boom. So what do we do next? Clock pulse, right? So we clock it again, boom. And this JK flip-flop remembers this 1. 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 And boom. And can you see, we're putting the input's coming in here, and it's sort of shifting it along these JK flip-flops every time we apply a clock pulse. And this is exactly the circuit that's used in a USB, basically any USB device, that's used to take this serial stream of 1s and 0s and make it into a nice parallel data stream that's ready for your device to use internally. So this is called a shift register, or a serial to parallel converter. Has anybody got any questions about this? Is it clear? Yeah? Want me to run over anything again? Just shout. I'm very happy to. We've got like 3 minutes. No? Okay. And it goes on and on, okay? So there we go. So here's a summary of today's lecture. Recap of last lecture, recap of gates, figuring out what electronic circuits do, make electronic circuits remember things, flip-flops, and serial parallel converters, okay? So thanks very much. I think you got me again this Thursday, and we'll just carry on like this. Have a nice week.